order is a vibration or acoustic response of a structure due to a rotating component. Okay, so when we talk about orders and order analysis, immediately we should start to think about rotation or rotating components. So to measure this, we would take a sensor, an accelerometer, or a microphone, and then we also want to track the rotation of a shaft using a tachometer. And let's say based on that reference shaft, it's spinning at 600 RPM. If we look at that shaft at 600 RPM, we can figure out the frequency of that because we have 600 rotations per minute. And we know frequency is a measure of 1/2. So we do some unit conversion here. We say 600 revolutions per minute is equal to 1 divided by 60, minute divided by second, right? So we convert that to revolutions per second. And then we have 10 revolutions per second. And if you remember, when we looked at that sine wave, we said the sine wave was 2 cycles per second. So in this case, we have revolution or a cycle per second. We could say it's 10 hertz. And we can plot that on a frequency plot here. A frequency of 10 hertz, we have a certain amplitude that we can measure and define on this plot here. If we increase the speed of that shaft to 6,000 RPM, we go through the same math, figure out the frequency, and here it'd be 100 hertz. And so we can measure that amplitude and plot it on that same graph that we just showed. At 3,300, the math gets a little more difficult. Might need to pull out a calculator, but again, we're going to figure out that that's at 55 hertz, and we'd have a measured amplitude. If we add a third axis to that plot we just showed, so now we have RPM, we have frequency, and we have amplitude, we can plot those 3 speeds that we just discussed, right? We have an amplitude at 600, we have an amplitude at 3,300, and we have an amplitude at 6,000 RPM. And the corresponding frequencies are shown here as well. So if we ramp through that speed, 600 to 6,000, then we can fill in all those blanks, connect the peaks, and that's what we would call an order cut, and it would be first order. The reasons it's first order is because we're looking at the shaft that we're measuring, so that's the reference shaft, and first order corresponds to something happening per 1 rotation. What we can do is just like what we did before we were looking at frequency and amplitude, looking at this waterfall plot that we're looking at, we could look down the RPM axis and amplitude, which is what's being shown up here in the corner. And we could see the vibration or acoustic response based on speed, and that would be called an order cut. And so we're looking at first order, that's all we've talked about so far. And what's unique about this, if you look at it, is we have, an increase in energy is what we would expect as the speed increases. But if you look here, there's actually a dip, kind of once we hit maybe 800 RPM or so, the energy actually dips down and then comes back up. And that's pretty typical when we look at an order cut. It's not a linear relationship in terms of, the faster I go, the more vibration I have. When we talk about orders, there's different frequency responses associated with that rotating machinery. And so when we're at a specific speed that's on a given frequency, that might be exciting a structural resonance. It might be exciting a structural resonance nearby the part we're concerned about. So we'll actually see kind of these dips and dives based on natural frequencies that are excited at different speeds. So we'll start to kind of complicate our system a little bit. If we look at shaft 1 and attach it to a second shaft, and we know that that pulley ratio is 3 times or 3-to-1 pulley ratio here. Now we can start looking at some relationships between those two, okay? So for instance, if we keep shaft 1 at 600 RPM, we know that shaft 2 is gonna go 1800 RPM based on that pulley ratio. And based again on the pulley ratio, we'll have a different frequency for shaft 2. So shaft 1 is spinning at 600 RPM, which we already calculated to be 10 hertz. Then we know with that 3-to-1 that shaft 2 will be spinning at 1800 RPM with a 30 hertz frequency. And so we can plot this on the same graph that we used for shaft 1. We have shaft 2 now with a frequency at 30 hertz and a measured amplitude. We go through those same speeds and we'll get a second plot. Now, this order cut has a name as well. So we we went through this math and we got our first order. So now that we have a pulley ratio of 3-to-1, we've got this second order cut highlighted here in the graphic, and that would have a name. And that name would actually be third order. The reason it's third order is because our reference shaft is shaft 1, and for every 1 rotation of shaft 1, shaft 2 spins 3 times. So we're getting 3 rotations per 1 rotation of our reference shaft. Now, if we moved our tachometer over to shaft 2, so now all speeds will be relative to shaft 2, this is going to change the way that we're looking at this information. So all these RPM values would now be referenced to shaft 2, and for every 1 rotation of shaft 2, we'd get 1/3 of a rotation of shaft 1. So we already said that the reference shaft where the speed is measured would be our first order. So this third order would switch to our first order. And because we're only getting 1/3 of a rotation per 1 full rotation of our reference, we get 1/3 order as that order to the left. And again, that's if we made the reference speed to shaft 2. Thanks.